The goal of this lecture is to show you the pushdown automata define exactly the context-free languages. So let's get to it. Besides the comfort of knowing that two seemingly unrelated concepts are really the same, the grammar PDA equivalence will let us jump between the two notations when we talk about properties of context-free languages. The ability to jump between different representations, regular expressions and deterministic finite automata, was important when we addressed properties of regular languages. And we shall find the ability essential for context-free languages as well. We also find it easier sometimes to describe a PDA for a language rather than a grammar. For example, you might find it hard to invent a grammar for balanced parentheses, but a PDA is easy to think of. Just push left parens onto the stack and pop the stack once every time you see a right parenthesis. If the bottom of stack marker is exposed, then the parentheses were balanced, and you never pop the bottom marker because that would mean you have more right parens than left. Let's start with a language L that has a context-free grammar G. We'll convert grammar G to a PDA P that accepts L by empty stack, and if you want a PDA that accepts L by final state, we know how to convert to one of those. P will have only one state Q, that's all we need. Naturally, Q is the start state. There are no final states because we are accepting by empty stack. The input symbols of P are the terminals of G. The stack symbols of P are all the terms and variables of G. And the start symbol of P is the start symbol of G. Our intent is that P will step through a leftmost derivation of input W from the start symbol S. The secret is that each left sentential form is represented in a subtle way. It is whatever input P has so far consumed, followed by whatever is on P's stack. When P reaches an empty stack, then the left sentential form it represents is whatever input it has consumed, followed by nothing, that is, by the empty stack. That means P has found a leftmost derivation of the input string it has read, so acceptance of the string is justified. If no sequence of choices of the non-deterministic P leads to empty stack after consuming W from the input, then W is not a terminal string derived by the grammar, and P rightly does not accept W. There are two kinds of rules in the transition function of P, depending on whether a terminal or variable of G is at the top of P's stack. The type 1 rules handle the case where A is the terminal on top of P's stack. There better be an A as the next input symbol, or P has guessed wrongly about the leftmost derivation of the input as it actually exists. In effect, we cancel the A on the stack against the A on the input. The left sentential form represented does not change. We have now consumed one more input symbol A from the input, so that becomes part of the left sentential form. But the A that was at the stack top is removed, so it no longer participates in the left sentential form. The type 2 rules handle a variable, say A, on the top of the stack. We need to expand that variable by the body of one of its productions and thus move to the next left sentential form. Of course, we're only guessing. We have to allow any of A's productions to be used. If A goes to alpha is one of these productions, then a choice for P using epsilon input and with A on top of the stack is to replace A by alpha. We're going to prove that P accepts exactly what G generates. Formally, we will show something more general. It seems we always have to show something more general than what we really want. Here we show that if P consumes W from its input, starting with only S on its stack, and winds up with stack alpha, that is, this ID becomes that ID, okay, then in G there is a leftmost derivation of the string W alpha. Incidentally, notice that as we describe the moves of P, we allow any string X to follow W on the input. Since no part of X was consumed, X cannot have any effect on the moves P made reaching the ID shown. So if the statement is true for one X, it is true for any other. That is, X does not matter. We start with the only if part. That is, if P makes the transition shown, then S derives W alpha in G. The basis is 0 steps. Then W is obviously epsilon since nothing can have been consumed from the input. And alpha is S since the stack doesn't change. We need to show that S derives W alpha in a leftmost derivation. But W alpha is just S, and surely S derives itself. Now let's do the induction. We'll consider the result of n steps of P, that is, this ID has become that ID, and we'll assume the inductive hypothesis for sequences of n-1 steps. We must consider type 1 and type 2 moves as the last step separately. First, consider the case where the last of the n moves is a type 1 move, where an A at the top of the stack is cancelled against an A on the input. Then the W consumed by the n move sequence must be of the form YA. That's this. And before the last move, the Y was consumed. That is, leaving just AX. Further, just before the last step, the stack of P is A alpha. By the inductive hypothesis applied to the first n-1 moves, we can conclude that there is a leftmost derivation from S of YA alpha. That's this, and it corresponds to the fact that there is an n-1 step derivation of that ID. But YA is W, so we already know that there is a leftmost derivation of W alpha. That is the needed conclusion for the full sequence of n steps. Now let's look at the case of a type 2 rule, where there is a variable A on the top of the stack after the n-1st move. After n-1 moves, P has consumed W from the input and has A beta on its stack. That's that. This, of course, is the ID after n-1 moves. At the nth move, no input is consumed, but A is replaced by gamma, one of its production bodies. Okay. That is, we assume A goes to gamma is a production. Okay. Notice that alpha is gamma beta here. That is, this stack string is really alpha. Okay. Again, we apply the inductive hypothesis to the first n-1 steps. We thus know that there is a leftmost derivation from S of WA beta. Since A is clearly the leftmost variable, and A goes to gamma as a production, there is also a leftmost derivation of W gamma beta. That's that. And of course, gamma beta is alpha, so that is really a derivation of W alpha, as we wanted to prove. We also should prove the converse, but we won't. That is, we need to show that if there's a leftmost derivation of W alpha, that is this, then P can consume W from its input with any unseen X following, and turn stack S into stack alpha. The proof is an induction on the number of steps of the derivation, but that's as far as we will take it. Assuming we complete the proof of the converse, we have the statement we set out to prove. P can consume W from its input with any X following, and turn stack S into stack alpha, if and only if G has a leftmost derivation of W alpha. Now we can restrict the statement to what we really care about, the case where X is empty, that is, P has consumed all its input, and alpha is also empty, that is, P has emptied its stack and accepted. We conclude that P consumes W while emptying its stack if and only if there is a leftmost derivation of W in G. That is, W is in N of P if and only if W is in L of G. For our next trick, we'll show how to convert PDAs to grammars. Assume language L is accepted by PDA P by empty stack. If it were accepted by a final state, we already know how to construct a new PDA that accepts L by empty stack, so we're entitled to assume acceptances by empty stack. We'll construct G, a grammar for L, and the idea is to give G variables, which we'll denote by pxq with brackets around them, like this. The job of this variable is to generate all and only the strings W, such that while reading W from the input, P goes from state P to state Q and appears to pop X from the input. While doing so, P can grow the stack well above where X was, but it can never go below where X was, and at the end the stack is shorter by 1 than it was when it started. That is, the net effect is that X has been popped. Here's a picture showing the height of the stack while X is effectively popped while reading W. Note that X might be replaced at the first move or later by another symbol Y. It could even be replaced many times, but the position of the stack that originally held X is never popped until the last move, right at the end here. As we mentioned, for every pair of states P and Q and stack symbol X, there is a variable that we represent by the composite symbol pxq. Although this expression consists of 5 characters, you must think of it as a single symbol in the set of variables of G. Also, as we hinted, the job of pxq is to generate all strings W that have the effect of taking PDA P in state P with only X on the stack to the ID where the state is Q, the input has been consumed, and X was popped. That's that. Notice that since the initial ID shows nothing below X on the stack, we know that X can't be popped until the last step, since PDA P cannot make any moves when its stack is empty. And there is one more variable of G, the start symbol X. There may be many productions for variable pxq. For each move of the PDA from state P with X as the top of the stack, we produce one or more productions. There are several cases, and they get increasingly more complex depending on how long the stack string is that replaces X at the first move. The easiest case is that of a rule that says in state P with input A, which could be epsilon or a real symbol, we pop X. That's that. Okay. There, X is replaced by 0 symbols. Then there is a production pxq goes to A. The reason this is correct is that reading only A is one way to have the net effect of popping X while going from state P to state Q. The next simplest case is when a move replaces X by a string of length 1, say Y. Suppose that move also changes the state to R. Then there is a production pxq goes to A RYQ. That is, one way to pop X while going from state P to state Q is to read input A, going to state R and replacing the X by Y at the top of the stack. Then some number of inputs, say W, has the net effect of popping the Y while going from state R to Q. As a consequence, the net effect of reading A followed by W is to take state P to state Q while popping the original X. Here's a picture of the case where X is replaced by a single symbol Y. How the Y gets popped we don't know, but when it does, the effect is that the symbol A followed by whatever W popped the Y has the effect of popping X while going from state P to state Q. Now it's getting a little more complicated. Suppose there is a move that replaces X by 2 symbols, Y and Z, while going to state R and reading A from the input. That is, the new stack YZ replacing X. In order for X to be erased, there must be some input string U that has the net effect of erasing Y, and U must take the PDA from state R to some state S, which unfortunately we don't know. As a result, we're going to have one production for each possible state S. But after reaching state S, we must have some additional input V that takes the PDA from state S to state Q while popping the Z from the stack. The net effect is that A followed by U and then V pops X from the stack while going from state P to Q. Okay. Here's a picture of that action. Initially you see X got replaced by Y and Z on the stack. Then U had the net effect of replacing Y, of popping Y, exposing the Z. Now we're in state S. And then V has the net effect of popping the Z and winding up in state Q. So we generate many productions for this case, where on input A, state P becomes R and X gets replaced by the stack, on the stack by Y and Z. For every state S, there's a production with head PXQ, and then the A that causes the first move. Remember, A could be empty. And then RYS to effectively pop the Y, winding up in this state S that we really don't know. So that's why there's one production for each S. And then SZQ to effectively pop the Z. We finally wind up in state Q, which is the state that we wanted to wind up because that's the state that appears in the head. As a result of this production, you can see that PXQ can derive any string AUV provided that RYS derives the U and SZQ derives the V. In the general case, where on input A in state P, X is replaced by a string of 3 or more stack symbols, Y1 through YK, and the state becomes R. We need a family of productions in which there are k-1 unknown states, S1 through Sk-1. Right. The productions all have this form. PXQ can be replaced by an A, which again may be epsilon, followed by variables R, Y1, S1, S1, Y2, S2, and so on, with the last of the variables being Sk-1, Yk, and finally the state Q from the head that we want to wind up in. With productions constructed in this manner, we can prove that P accepts W by empty stack. That is, the ID Q0 W Z0 goes to P epsilon epsilon if and only if the variable Q0 Z0P derives W. We're not going to give the proof. It is 2 easy inductions, one for each direction. The only problem is that we don't know state P. But remember, G has another variable S, and that is the start symbol. So we add production S goes to Q0 Z0P for every state P. And now we have a grammar that generates exactly the strings that the PDAP accepts. There is a pumping lemma for context-free languages analogous to the pumping lemma for regular languages. The goal of this lecture is to state and prove this lemma, which is naturally more complicated than the pumping lemma for regular languages, and then use it to show certain languages are not context-free. Let's review the pumping lemma for regular languages. It said that any sufficiently long string W in a regular language has some short, non-empty piece near the beginning that we could pump. That is, we could repeat it as many times as we liked, including 0 times, and the resulting string would also be in the language. We found the string to pump by looking for the first state to repeat as a finite automaton process that's input W. The pumping lemma for context-free languages says that we can find 2 pieces in any long string Z and pump them in tandem. That is, we can repeat each of them I times for any I equal to or greater than 0, and the result will be in the same language. We'll also see that these 2 strings are close together in Z, and one can be empty, but not both. Here's the statement of the pumping lemma for context-free languages. We can see it as the same sort of game with an adversary that we talked about in connection with regular languages. For every context-free language L, that is, you get to pick L, presumably the one you want to show isn't really context-free, there is an integer n. This is something the adversary gets to pick, but once it's picked, it's fixed for the rest of the game. Such that for every string z in L of length at least n, and here you get to pick the z to focus on, you can break z into 5 pieces, u, v, w, x, y, such that 3 things are true. The adversary gets to pick how z is broken, but subject to 2 constraints we'll see in just a moment. And incidentally, v and x are the substrings that get pumped. The first constraint is that the middle 3 components, v, w, and x, are short, no longer than the length of n put together. Remember that v and x will get pumped, so that says not only are they short, but they appear within a bounded distance from each other within z. The second condition that the adversary has to respect is that v and x cannot both be empty, although one can. And if all the above is satisfied and L really is context-free, then for all integers I equal to or greater than 0, u, v to the I, w, x to the I, y is also an L. We win the game and prove L is not context-free by allowing the adversary his choices of n and the breakup of z subject to the constraints 1 and 2, and then picking an I such that u, v to the I, w, x to the I, y is not an L. The proof of the pumping lemma for context-free languages starts with a Chomsky normal form grammar for L. Technically it is for L minus epsilon, but the empty string will never meet the condition of being of length at least n, so its presence or absence doesn't matter. This CNF grammar has m variables for some m, so we're going to let n be 2 to the m. And now let's consider any string z in L of length at least n. That's 2 to the m again. We're going to prove first that any parse tree in a CNF grammar for a string z of length at least n equals 2 to the m must have a path of length m plus 2 or more from the root to a leaf. We'll actually prove the contrapositive. That is, suppose there is a parse tree z with no path longer than m plus 1. Such a path has m nodes labeled by variables at the top, or the beginning, and one node labeled by a terminal at the end. That is, here is a typical path. It will have variables here, here, and here, and then a terminal there. Okay. If we forget about the terminals at the leaves, a parse tree in a CNF grammar is a binary tree. Thus, at each level, the number of nodes can at most double. Thus, there is only one node at the top level, the root. There can be only 2 nodes at the next level, 4 at the third, and 8 at the fourth, and so on. In general, there'll be at most 2 to the power m minus 1 at the nth level. But this tree has at most m levels with variables, and then along each path of variables, the last variable has one child with a terminal as its label. The largest number of leaves occur if all the paths in the tree have exactly m variables. If some paths terminate before level m, there will be fewer leaves. Thus, there are at most 2 to the m minus 1 nodes that are labeled by variables and have a single child with a terminal label, and thus there are at most 2 to the m minus 1 leaves. Finally, we therefore can conclude that the length of the yield is at most 2 to the m minus power m minus 1. Now 2 to the power m minus 1 is n over 2. Since z is of length n, it cannot be the yield of any tree that has paths limited to length m plus 1 or less. Therefore, we conclude that somewhere in the parse tree for z is a path of length at least m plus 2. Now we're ready to prove the pumping lemma. We just proved that z's parse tree has a path of length at least m plus 2. Only the last node in any path can be labeled by a terminal, so there are at least m plus 1 nodes with variables along this path. Let's focus on one of the longest paths in the parse tree for z. Surely there are at least m plus 1 variables along this longest path. Remember that m is the number of variables of the grammar, so along this path there are 2 nodes labeled by the same variable. Call it a. In fact, to make sure we pump short pieces, let's look only at the bottommost n plus 1 variables along this path, which could be much longer than n plus 1, and we know that 2 of them must be the same. On the next slide, we'll see what the parse tree must look like. Here's a picture of the parse tree for Z. We've shown the path we've focused on and the lowest repeating variables along that path. The purple tree is rooted at the lower A, and the yellow tree, with the purple tree within it, is rooted at the upper A. Let W be the yield of the purple tree. V and X are the portions of the yield of the yellow tree that precede and follow W, respectively. And let U and Y be the portions of Z that precede V and follow X, respectively. Let's look at the yellow. Since the path shown is as long as any other, and that path has at most n plus 1 variables, we know by the lemma 1 that we just proved that the yield of the yellow plus purple is no longer than 2 to the power m, or n. That is, the length of VWX is no more than n. But V and X both can't be empty. Why? That's a useful property of Chomsky normal form grammars. Since the two A's shown in the tree are different nodes, the upper A must have a child to the left or right of the path shown. That's a consequence of the fact that we eliminated unit production, so all bodies that have variables have at least 2 of them. Moreover, once we have a variable not on the path, there are no epsilon productions, so we must generate from this variable at least one terminal. That is all we need to conclude that either V or X or both have length at least 1. Now we can take advantage of the fact that we have 2 A's along the path. We can get rid of V and X by pumping 0 times. That is, we know the purple tree can substitute for the yellow because both trees have the same variable A at the root. If the original on the left satisfies the conditions of a parse tree, that is, every interior node is the head of a production whose body is the labels of its children, then the same will be true of the smaller parse tree on the right. We conclude that UWY is also in the language. Or we could pump twice, that is, replace the purple tree by the yellow, which has the purple within it, and we get a parse tree whose yield is UVVWXXY. And in the previous tree representing pumping twice, we could again replace the purple tree by the yellow and get a bigger tree whose yield is U, 3 V's, W, 3 X's, and then Y. In the same manner, we can get parse trees for all strings with the form U, V to the I, W, X to the I, Y for any integer I equal to or greater than 0. These strings are therefore all in the language L. That proves the pumping lemma for context-free languages. Let's look at an example of how the pumping lemma can be used to show a language not to be context-free. This language, which involves matching the counts of 2 blocks of zeros, is context-free. A grammar or PDA for it is easy to construct. The ideas are very much like what we saw for the language 0 to the n, 1 to the n. But give the language 3 blocks of zeros, all of which must be the same length, and we're suddenly outside what context-free grammars can do. We can prove that using the pumping lemma for context-free languages. So we'll pick this language L, and the adversary now gets to pick n. We don't know n, but we do know it is fixed for the rest of the game. We get to pick z, so let's pick 0 to the n, 1, 0 to the n, 1, 0 to the n. That is, each block of zeros is of length equal to whatever n the adversary picked. Now the adversary gets to break our z up into z equals UVWXY, but he must choose these substrings such that VWX together are no longer than n, and V and X cannot both be picked to be the empty string. There are 2 cases depending upon whether the adversary picks V and X to have zeros or not. In the first case, suppose there are no zeros among V and X. Then since they cannot both be empty, there must be at least one 1 among them. But then, if we pump 0 times to get the string UWY, we know that there is at most one 1 in this string. The pumping lemma claims it is in the language L, but it can't be because all strings in L have exactly 2 1s. In the second and last case, V and X have at least one 0 among them. VWX has length at most n. So these three substrings cannot extend from the first block of zeros to the last because n plus 2 positions separate those blocks. So again consider UWI, which if L is context-free must be in L. Removing V and X must leave at least one of the three blocks of n zeros intact, so it still has n zeros. But V and X have at least one zero, so in UWY, at least one of the blocks of zeros has fewer than n zeros. We conclude that in this case too, UWY cannot be in L, and thus L cannot be context-free. To finish off our discussion of context-free languages, let's look at the properties of this class of languages. Remember, there are two kinds of properties we find useful. One is decision properties, where we tell something about a language or languages in the class, such as whether the language represented by a grammar or PDA is empty. And the other is closure properties, where we prove that some operation, say union, applied to languages in the class, results in another language in the class. First, let's remember that when we talk about a decision property or a closure property for a language class, we're talking about algorithms that take a representation for a language in the class and produces an answer. For the regular languages, we use regular expressions and deterministic finite automata as the representations. Here, for context-free languages, we use the context-free grammar or the pushdown automaton as the representation, whichever makes life easier. And when we use the PDA, we can let acceptance be by final state or empty stack, again, whichever makes life easiest. Here are some questions about context-free languages for which algorithms exist. Given a representation for a context-free language, L, and a string W, we can determine whether or not W is in L. We can tell whether a representation for a context-free language, L, generates the empty language. And we can also tell whether this language L is finite or infinite. Unfortunately, many of the things we can decide about regular languages, we cannot decide for context-free languages. For example, we were able to tell whether two regular languages, say represented by DFAs, were the same. We can't tell whether two context-free grammars or two PDAs define the same language. Another thing we cannot tell is whether two context-free languages are disjoint. We say sets are disjoint if their intersection is empty, that is, they have no members in common. We didn't address the question of disjointness for regular languages, but you can tell whether two regular languages are disjoint. We showed regular languages are closed under intersection using the product automaton trick. We also showed that you can tell whether the language of an automaton is empty. These two ideas together give you an algorithm to test whether two regular languages are disjoint. At this point, we have no way to prove that no algorithm for a task exists. That is the job of the theory of Turing machines and decidability, and that will be the next big topic that we address. Now, the emptiness test for context-free languages has already been given in essence. We showed how to eliminate useless symbols, those that participate in no derivation of a terminal string. Take any context-free grammar and see whether or not the start symbol is useless. If so, the language of the grammar is empty, and if not, then not. The membership test for DFAs was really simple. We just simulate the DFA on the string. We can also test whether a terminal string W is generated by a grammar G, but the test is remarkably hard by comparison. We'll assume G is a grammar in Chomsky normal form. If not, we know how to convert the given grammar to CNF, so let's do that as the first step. There's a small matter that when we convert to CNF, we lose the ability to generate the empty string. But if W, the string we want to test, is epsilon, then there is another approach entirely. Apply the algorithm we learned for finding the nullable symbols, those that derive epsilon. See if the start symbol is one of these, and that lets us test membership of the empty string in the language of a context-free grammar. We're going to give an algorithm called CYK. The initials stand for the three people who independently invented the idea: John Koch, Dan Younger, and Tadao Kasami. This algorithm is a great example of a dynamic programming algorithm and worth seeing for that reason alone. The running time of the algorithm is of the order of n cubed, where n is the length of the input string w. Incidentally, there is another algorithm due to J early that also runs in time order n cubed, but on an unambiguous grammar, Early's algorithm is faster. It's order n squared. However, the CYK algorithm is much simpler, and as I said, worth studying because it is a model for so many useful dynamic programming algorithms. So that is the one we're going to learn. Here's how the CYK algorithm works. Start with an input string of length n. Let a sub I be the symbol in the ith position. We're going to construct a triangular array with short sides each of length n. Each entry in the array is a set of variables of the grammar. The set x sub ij, which will be in position ij, and I is equal to or less than j, is intended to be the set of variables A that derive the substring of the input, starting at position I and ending at position j. That is this. We'll use an induction to fill the table. The induction is on the length of the string derived, which is j minus I plus 1. So we start by computing the entries x sub I, which is the set of variables that derive the string consisting of the one position ai. From these we can find the I plus 1s, each of which is the set of variables that derive the string ai followed by ai plus 1. Then we move to the I plus 2s, which are the sets of variables that derive the strings of length 3, ai plus 1, ai plus 2, and so on. Finally, after we have computed the one set x1n, which represents the entire input, we can ask ourselves whether s is in that set. If so, then s derives a1 through n, and the string w is in the language, and otherwise not. For the basis, we know that the only way to derive a string of length 1 in a CNF grammar is to use a production whose body is a single terminal. So for each I, we can set xii to the set of variables a, such that a goes to ai is a production. For the induction, where j is strictly greater than I, we can compute xij from x's representing two substrings of ai through aj. The first is the substring from ai to ak for some k less than j, and the second is ak plus 1 through aj. Both these strings are of length less than j minus I plus 1, so we have already computed the sets x sub ik and x sub k plus 1j. In order for a variable a to derive ai through aj, there must be some production, say a goes to bc, where b derives ai to ak, and c derives the rest. That is, for each k between I and j minus 1, we look for some b in xik and some c in xk plus 1j, such that bc is the body of an a production. If for any k, b, and c we find such a production, we add a to xij. We're going to do an example of the CYK algorithm. Here's the CNF grammar we'll use, and the input string w will be ABABA. It is of length 5, so we're going to compute sets of variables xij for I less than or equal to j, and I equal to greater than 1, and j less than or equal to 5. That's a triangular array. For the basis, let's see which variables have a production whose body is a. These variables are capital A, has this production, and capital C, which has that production. Thus, if W has the symbol little a in position I, then XII will be AC. We see A in positions 1, 3, and 5 of W, so that explains X11, X33, and X55. For terminal B, we see body B in productions for B and C. That's here and here. Thus, if I is a position of W that holds B, XII will be BC. That explains positions 2 and positions 4. Now we need to compute the 4 entries in the row above. These are the sets of variables that derive substrings of length 2. Here's one example, x12, which is the set of variables that derive the string in the first positions of W, that is, AB. When j is I plus 1, k can only be I. That is, the only way to derive a string of length 2 in a CNF grammar is to use a production where one variable is replaced by 2, and each of these variables derives one terminal. So the reason S is in x12 is that A is in x11, B is in x22, and S goes to AB is a production. And the reason B is in x12 is that A is in x11, C is in x22, and B goes to AC is a production. Notice that C can't be in x12 because C derives only strings of length 1. However, A can derive long strings and yet is not in x12. The reason is that the only production A has with a body of 2 variables is A goes to BC. That's this. In order for A to be in x12, we would need to find B in x11 and C in x22. The latter holds, but B is not in x11. Here are the other 3 sets for the row corresponding to the substrings of length 2. We'll leave it to you to verify that those are correct. Now let's start computing x13. A string of length 3 can be broken in 2 different ways, either a string of length 1 followed by a string of length 2, or vice versa. In the first case, k equals 1, and we must combine x11 with x23. x11 has A and C, while x23 has only A. The only bodies we can form from these are AA and CA. But no variable has a production with either of these as the body. Thus k equals 1 gives us nothing. We must also consider k equals 2, where we combine x12 with x33. Now there are 4 possible bodies, B or S followed by A or C. Of these, only BC is a body of a production of our grammar, and its head is A. Thus, x13 turns out to be just the set containing A. Here are the other 2 x's for substrings of length 3. There is a pattern to computing these corresponding to the choices of k that we may make for each. We start at the bottom of the column. For example, for x24, that would be x22. And we start going down the diagonal to the right. For x24, that would be x34. So we're going to pair x22 with x34. We then pair them to see what production bodies we can form, and then we move up the column, here in this case to x23, and down the diagonal, in this case, to x44, and we pair these 2 guys to again see what variables we can form from that one followed by that one. Here's how we compute x14. Starting at the bottom of the column, that is x11, and the top of its diagonal, that is x24. We pair these to see if we can form any production bodies. In this case, we can combine A from x11 and B from x24 to put S, the head of the production with body AB, into x14. Now we move up the column to x12 and down the diagonal to x34, but pairing B or S with B or S doesn't give us any right sides. So we proceed up the column to x13 and down the diagonal to x44, and we pair A with B or C. AC is a body, and it justifies our putting B into x14. Here are the last 2 entries in the triangular table. x25 turns out to be the set containing A. We'll let you check that one out. And x15 is also A. We get A from x14, which has B, and x55, which has C. BC is a body, and A is its head. Since S is not an x15, we conclude that ABABA is not in the language of the given grammar. We also claim that there is an algorithm to tell whether a context-free language is finite or infinite. We won't give the algorithm in detail, but it is essentially the same as the time-consuming algorithm we gave for regular languages. We use the pumping limit constant n, and as for regular languages, we can show that if a context-free language contains any string of length between n and 2n minus 1, then that string can be pumped and the language is infinite. Otherwise, the language is finite. We're now going to enter the area of closure properties, and for many of the same operations under which the class of regular languages are closed, the context-free languages are also closed. These include the regular expression operations themselves, union, concatenation, and closure, and also reversal, homomorphism, and inverse homomorphism. But unlike the class of regular languages, the class of context-free languages is not closed under intersection or difference. Here's a proof that the union of two context-free languages is a context-free language. Let L and M be the context-free languages, and let them have grammars G and H respectively. We need to rename variables of one of these grammars, so no variable is used in both the G and H. The names of the variables don't matter, so we can always do this. The reason it is so important is that we're going to throw the productions from G and H into one pile, and if they had variables in common, we could accidentally use a production from G on a variable from H or vice versa. Note that we do not change the terminals of the grammars. It's okay if they have terminals in common. In fact, we expect that they will have terminals in common. Suppose S1 and S2 are the start symbols of the two grammars after renaming the variables. And we'll build the grammar for L union M by combining all the symbols of the two grammars G and H. That is, the new set of terminals is the union of the terminals of G and H, and the new set of variables is the union of the variables in G and H, plus a new symbol S that is not a symbol of either grammar and will be the start symbol of the new grammar. The new set of productions is the union of the productions of G and H, plus two new productions, S goes to S1 and S goes to S2. All the derivations of the new grammar start with S. And in the first step, this S is replaced by either S1 or S2. If S is replaced by S1, then the entire derivation must be a derivation of G, because we cannot then get any variables of H into our derivation. Similarly, if the first step gives us S2, then the entire derivation is a derivation of H. Thus, the terminal strings derivable from S are exactly those in L if we start with S goes to S1. Union those in M if we start with S goes to S2. That is, the new grammar's language is L union M. The argument that the class of context-free languages is closed under concatenation starts the same way, with grammars G and H for the languages L and M. These grammars are assumed to have no variables in common and to have the start symbols S1 and S2 respectively. Again, we combine the two grammars as we did for union. The only difference is in the productions we use for the new start symbol S. Here there's only one production, S goes to S1 followed by S2. That way all strings derived from S will be a string of L followed by a string of M. That is, the new grammar will generate L concatenated with M. For Kleene star, let's start with the grammar G for the language L. Let this grammar have a start symbol S1. Form a new grammar by adding to G a new start symbol S and the productions S goes to S1S or the empty string. Then a rightmost derivation from S begins by generating 0 or more S1s, that is, it uses this production as many times as it likes, followed by S goes to epsilon. From each of these S1s we can generate exactly the strings in L, so the new grammar generates L star. Reversal is another operation for which it is easy to show closure using grammars. If we have a grammar G for the language L, we form a grammar for L reversed by reversing the bodies of all the productions of G. For example, here is a grammar for the language 0 to the n, 1 to the n. If we reverse the bodies, we get this grammar. It is easy to see that this grammar generates all strings of one or more ones followed by the same number of zeros. That language is the reverse of the language we started with. We're not going to give a proof that this construction works. It is a simple induction on the lengths of derivations in the two grammars. To prove closure of the context-free languages under homomorphism, let's start with a grammar G for a language L and let H be the homomorphism on the terminal symbols of G. Then H of L has a grammar that we can construct by replacing each terminal A in the body of any production of G by the string H of A. So for example, here G is our customary grammar for 0 to the n, 1 to the n, and here's our usual example of a homomorphism. Then H applied to the language of G has a grammar in which the two occurrences of 0 in the productions of G are replaced by AB, and the two occurrences of 1 are replaced by the empty string. Notice that the resulting language is all strings of one or more ABs. It is in fact a regular language, although in general we can only be sure that it will be a context-free language. Next, we take up the fact that context-free languages are closed under inverse homomorphism. While we seem to have done pretty well using a grammar as the representation for context-free languages so far, here we really need the PDA representation. Start with a PDA P that accepts the language L by final state. We'll construct another PDA P prime that accepts H inverse of L, where H is some homomorphism. The big idea is that P prime will simulate P, but P prime needs to apply H to every input symbol it sees, and since H of A may be a long string, P prime has trouble simulating P in one move, and often it cannot do so. So P prime will take it one step at a time. It has a state with two components. The first is the state of P, which is important in the simulation. But the second is a buffer that holds a suffix of what you get by applying H to some one symbol. This buffer allows P prime to use the symbols of H of A one symbol at a time to cause moves of P. Here's a rough sketch of what P prime looks like. As mentioned, its state has two components, the state of P and the buffer. We show input 0, 0, 1, 1 as an example only. Now P prime can read its first input symbol, 0, and apply H to it. The buffer, which was initially empty, now has the string H of 0. It may be a long string, but its length is finite, so there is only a finite number of states P prime can be in. Now to simulate P, P prime takes the first symbol of H of 0 and simulates P using that as the next input symbol. The simulation could take many moves, as there can be transitions on epsilon input as well as one transition on the symbol itself. However, the symbol is removed from the front of the buffer, so the next time P needs a real input symbol, it gets the second symbol of H of 0. The simulation proceeds in this manner until all symbols of H of 0 are consumed from the buffer. At that point, P prime can apply H to its next input and refill the buffer. To be more precise, the states of P prime are pairs QW, where Q is a state of P, and W is a suffix of H of A for some symbol A. Note that given P and H, there are only a finite number of values of W, and of course P has a finite number of states Q, so P prime also has a finite number of states as is required for any PDA. The stack symbols of P prime are those of P. Moreover, as we shall see, the stack behavior of P prime mimics that of P. And the start state of P prime is Q0 epsilon, that is the start state of P paired with an empty buffer. The input symbols of P prime are those symbols A for which H of A is defined, and the final states of P prime are the final states of P paired with an empty buffer. Now we'll show how P prime simulates P by giving the transition function delta prime for P prime. The first type of transition allows P prime to read an input symbol A, which must not be epsilon, apply H to it, and store it in the buffer. The buffer of P prime must be empty for this to happen, although since P might be able to make moves with epsilon input, P prime is not forced to refill the buffer just because it is empty. It can also make moves without consuming its own input. Formally, delta prime of Q epsilon A and X, this, has one choice. It can remove the A from its input. Again, remember A is not empty. Place H of A in the buffer and leave its stack and state unchanged. Note that H of A might be empty, in which case the buffer remains empty, but it is also possible that the buffer now contains one or more of P's input symbols. P prime also has the option to ignore its own input and simulate P as if P's input were whatever it is in the buffer. Formally, suppose that delta of Q, B, and X contains P alpha. Here B may be epsilon or it may be an input symbol of P. And then for any buffer string of the form BW, that is a suffix of H of A for some A, delta prime of Q in the buffer BW with no input, this epsilon input, and X on the top of the stack will contain PW alpha. That is, B is consumed from the front of the buffer, the state of P changes according to the given choice of P's move, and the stack of P prime also changes in accordance with that given move. In order to prove that P prime does what we want it to do, that is, accept H inverse of the language of PDAP, we need to do two inductive proofs, one in each direction, of the statement that characterizes the way in which P prime simulates P. We're not going to give the proofs here. The precise statement of P prime simulates P is given in the middle of the slide. It says that P prime goes from its initial ID with input X, that's this, to some ID with state Q of P, buffer contents X, W consumed from the input, and alpha on its stack, and that's this, if and only if, well, first of all, P goes from its initial ID with input Y, that, to an ID that has state Q, input Y consumed, and alpha on its stack, that's that. And second, H of W is Y, that's what P consumed, followed by X, which is the thing that P prime still has left in its buffer. Once we have that, we can restrict it to this case where X is empty and Q is a final state. It then says that P prime accepts W if and only if P accepts H of W. That is, the language of P prime is H inverse of the language of P. We have not yet addressed intersection. Remember that the regular languages are closed under intersection, and we proved it by running DFAs for the two languages in parallel. But we can't run two PDAs in parallel and still have a PDA. The reason is that the parallel execution of two PDAs requires two separate independent stacks, and a PDA is only allowed to have one stack. That's only an argument that the obvious first try at proving context-free languages are closed under intersection won't work, but the situation is worse. We can see particular context-free languages whose intersection is not a context-free language, so no construction could possibly work. We said that this language, L1, the set of strings with some number of zeros followed by the same number of ones and the same number of twos, is not a context-free language. The pumping lemma gives us an easy proof of that fact. We're not going to do it here, but it's very much like the example of the pumping lemma proof that we did give. But consider L2, the set of strings in 0 star, 1 star, 2 star, that is, strings of zeros followed by some number of ones followed by some number of twos, such that the number of zeros and ones are the same with any number of twos. This language is context-free, and here is a little grammar for it. The job of variable A is to generate zeros followed by an equal number of ones. We've seen this mechanism several times before, and B generates just any number of twos, at least one of them. Now let L3 be the set of strings in 0 star, 1 star, 2 star with equal numbers of 1s and 2s and with any number of zeros. This language is also context-free, and the grammar for L3 uses the same ideas as the grammar we just showed for L2. But L1 is the intersection of context-free languages L2 and L3. We can also show that the difference of two context-free languages is not necessarily context-free. In fact, we can prove something surprising. Intersection can be expressed in terms of difference alone. Therefore, if any class of languages is closed under difference, it is also closed under intersection. The argument is that the intersection of any two languages, L and M, regardless of whether they're regular, context-free, or not context-free, is the difference between L and L minus M. That is, suppose X is in L intersect M. Okay, then X is surely not in L minus M because it's in both L and M, and therefore X is in L and not in L minus M. Therefore, it is in this expression on the right side. That proves containment in one direction. For the other direction, suppose X is in L minus M. That's this guy here. Then X is in L, and it's not in L minus M. But if X is in L but not in L minus M, it must be that X is also in M. Thus, X is in L intersect M. That proves containment in the other direction, that is, X here implies X there, and that proves the equivalence of these two expressions. Now, suppose the class of context-free languages were closed under difference, and L and M are context-free languages. Then L minus M would be context-free, and so would this guy, L minus M. But we just proved that this expression is the same as L intersect M. Thus, context-free languages would be closed under intersection, but we know they're not, so we know they could not be closed under difference either. We know that the intersection of two context-free languages may not be a context-free language. However, if we intersect a context-free language and a regular language, then we always get a context-free language. The idea is to run a DFA in parallel with a PDA. Since the DFA has no stack, we do not face the problem of trying to simulate two stacks with one that we face if we try to run two PDAs in parallel. Here's the picture of a PDA and a DFA running in parallel. We can combine the states of the two automata to make one state for a new PDA. It manipulates the stack of the original PDA and feeds inputs to both the original PDA and the DFA. It accepts if both the PDA and the DFA accept. To give the construction of the new PDA, let the DFA have a transition function delta A, and the original PDA will have a transition function delta P. States of the new PDA will be pairs. The first component, Q, is a state of the DFA, and the second component, P, is a state of the PDA. Suppose the original PDA has a choice of move from state P and stack symbol X, where A is consumed from the input. That's this. A could be a real symbol or epsilon. The result of the move is that the PDA state becomes R, and X on the stack is replaced by alpha. That's the move. Then the new PDA, whose transition function we call simply delta, given a state with P as the second component, input A, and stack symbol X, that's this, has a choice of move where the new state has second component R. The first component is what you get by having the DFA make a transition from state Q with input A. That's delta A of Q and A. Note that A could be epsilon here, in which case delta A of QA is just Q, or it could be a real symbol in which delta A of QA is something else. Finally, this choice of move replaces X by alpha on the stack, just as the original PDA did. The final states of the new PDA are the pairs QP, such that Q and P are final states of their respective automata. And the initial state of the new PDA is the pair consisting of the initial states of both automata. We need to prove a pair of inductions on the number of moves made by each PDA. These inductions say that the new PDA started in its initial state with input W, this, consumes the input and enters an ID with state QP, okay, and stack alpha, having consumed the input. Okay, and that happens if and only if the original PDA goes from its initial ID with input W to the ID with the same state P and alpha on the stack. And of course the DFA goes from its initial state on input W to the state Q. We'll skip the details as the proofs are not too hard. We're now changing the subject matter considerably. Until now, I've been talking about simple models such as finite automata or context-free grammars that let us model mechanisms like communication protocols or processes like the parsing of programming languages. Today we begin to study the other side of automata theory, the part that lets us show certain tasks are impossible, or in some cases possible but intractable. That is, they can be solved, but only by very slow algorithms. It might not be obvious, but just because we can state a problem doesn't mean there is any algorithm at all that can solve it. For example, can you devise an algorithm to tell whether the complement of a context-free language is empty? That is, does a grammar generate all strings over its terminal alphabet? It turns out you can't. And we're going to learn the theory that lets us prove facts of this kind. We begin with a central theme of the study of what can be solved by computer algorithms. The idea that all data can be represented by integers. The idea of countable sets, those whose members can be assigned integers 1, 2, 3, and so on, is essential here. We're going to meet the Turing machine, which is in some sense the ultimate automaton. It is a formal computing model that can compute anything we can do with a computer or with any other realistic model that we might think of as computing. Turing machines define the class of recursively enumerable languages, which is thus the largest class of languages about which we can compute anything. There's another smaller class called the recursive languages that can be thought of as modeling algorithms, computer programs that answer a particular question and then finish. I realize the concepts are vague at this point, but we'll get to it all in good time. If you took a modern course on programming, you are undoubtedly introduced to the importance of data types or classes. But when you look under the hood, how these types are represented inside the computer, you see that there is only one type, strings of bits. We could base our whole theory on strings of bits, but it is more convenient to convert binary strings to integers. We can almost see how to do that, since integers can be represented in binary notation, but there's a small glitch we'll get to. And to make the idea that all the world is integers even more pervasive, remember that the programs that computers execute are also, under the hood, just strings of zeros and ones, and therefore can be regarded as integers. That lets us talk about the 100th program and things like that. As we shall see, the fact that programs and data are at heart the same thing is what lets us build a powerful theory about what is not computable. As a simple example of a type that is really integers, let's look at character strings. Strings of ASCII characters can be thought of as binary strings, 8 bits to a character. Or if you use Unicode, you need 16 bits per character, but the idea is the same. Strings in any alphabet can be represented by binary strings. And binary strings are really integers. Thus, it makes sense to talk about the ith string for any I. However, we have to be careful how we do the conversion from binary strings to integers. Because binary strings can have leading zeros, there is not a unique representation of an integer as a binary string. More to the point, if you do the obvious conversion, then strings like the ones shown all seem to be the integers 5. But we can't call 2 or more different strings by the same integer. However, there is a correspondence between binary strings and integers that is one-to-one and almost as simple. Put a 1 in front of any binary string and then treat it as an integer. This way, no two strings can correspond to the same integer. For example, if we're given string 101, then put a 1 in front of it and treat 1101 as a binary integer, and you'll get 13, by the way. If you put a 1 in front of 0101, then this integer is 21, and so on. For a wilder example, consider images as a data type. There are many representations of images. Let's talk about GIF. A GIF file is an ASCII string, so convert ASCII to binary, and then the binary string to an integer in the way we just discussed, and bingo, you have a notion of the ith image. Here's another wild example, proofs. A proof can be viewed as a sequence of expressions or assertions in mathematical form, each of which is either given or follows from previous statements in the sequence by certain logical rules. We can encode mathematical expressions in Unicode. It has pretty much any symbol you would use in mathematics. But we can convert any expression to a binary string and thus to an integer. There is again a small glitch. A proof is a sequence of expressions, not a single expression, so we need to fix on a way to separate a sequence of expressions. We also need to indicate whether an expression is given or follows from previous expressions. We thus need to introduce two new symbols into our strings. One is a comma to separate expressions. We can't just use the Unicode comma because the expressions themselves may use this symbol. The other is a marker that says, this is a given expression. The following technique is useful not only here, but in general as a way to introduce new symbols with any meaning into binary strings while still keeping the strings binary. First, given a binary string, expand it by inserting a 0 in front of every bit of the string. For example, 101 becomes 01, that's the first one, 00, that's the 0 in the middle, and then 01. Now, as a consequence of this change, strings have no consecutive ones. Use strings of 2 or more ones as the new symbols. For example, we'll use 111 to mark a given expression and 11 as the marker for the end of an expression. Here's an example of what a proof as a binary string could look like. The initial 111 can only mean that the expression to follow is a given expression. Here is the expression itself. It was originally 101, but we expanded it with a 0 in front of each symbol. Of course, 101 is too short to really be an expression, since even one Unicode character takes 16 bits, but let's not worry about that. This 11 marks the end of the first expression. Notice that this 1 cannot be part of a special marker, since all expressions without the special markers have even length, and this 1 is the 6th symbol in the expression. Here's another given marker. And another expression. This one was 0011 with zeros embedded. And another expression ender, and so on. As we said, programs in a language like C or Java are also a data type and can be represented by integers as if they were data. First, represent the program as an ASCII string or in some other alphabet like Unicode if the language requires it. Then convert the character string to a binary string and then to an integer. Now we can talk about the ith program. And this should worry you. There really aren't more programs than there are integers. While that number is infinite, you may be aware that there are different orders of infinity, and the integers are the smallest one. For example, there are more real numbers than there are integers, so there are more real numbers than there are programs. That immediately tells you that some real numbers cannot be computed by programs. We'll get to more concrete explanation of what the dearth of programs really means shortly. We have an intuitive notion of when a set is finite or infinite. A set is finite if there is a particular integer that is the count of the number of members of the set. The term for the count of the number of members is cardinality. For example, the set containing A, B, and C is a finite set, and its cardinality is 3. The formal definition of a finite set is one for which it is impossible to find a one-to-one correspondence between the members of the set and a proper subset of that set. Well, actually, the formal definition of an infinite set is one for which there is a one-to-one correspondence between its members and a proper subset. Then the finite sets are formally the sets that are not infinite. For an example, the positive integers are an infinite set. We can let the proper subset be the even integers, and the one-to-one correspondence matches 1 with 2, 2 with 4, 3 with 6, and so on. Every positive integer I is matched with a unique even integer 2i. A countable set has a one-to-one correspondence with the positive integers. For example, the set of all integers, positive or negative, is countable. A correspondence maps 0 to 1, minus I to plus 2i for all I equal to or greater than 1, and plus I to 2i plus 1 for all I equal to or greater than 1. As a consequence, the positive and negative integers get interleaved in the ordering as 0, minus 1, 1, minus 2, 2, and so on. The binary strings are also countable. We saw how to assign a unique positive integer to each binary string by putting a 1 in front and treating the result as a binary integer. Likewise, the Java programs can be put in one-to-one correspondence with binary strings and then with integers. Many of these integers represent flawed Java programs, things that don't compile, but that is not important. The important thing is that every working Java program has a unique integer. A rather surprising point is that pairs of integers can be put in one-to-one correspondence with the integers themselves. A simple way to see this is to explain an ordering of the pairs as first pair, second pair, and so on. The ordering we want is first by sum, and then for pairs with the same sum by first component. Thus, 1, 1 comes first. It is the only pair with a sum of 2. There are 2 pairs with a sum of 3, these guys, and we put 2, 1 ahead of 1, 2 because it has the higher first component. Then come 3 pairs with sum 4, these 3, again ordered by the first component. You can, in fact, figure out a function f of ij such that the pair ij is the f of ijth in that order. But the important point is that some such function exists, and therefore it makes sense to talk about the ith pair of integers. We call the one-to-one correspondence between a countable set and the positive integers an enumeration of the set. Thus, strings, programs, proofs, and pairs of integers, for example, have enumerations. Now, let's look at the set of all languages over some fixed alphabet, say 0, 1. Could this set be countable? The answer is no, and we can prove it. Suppose it were possible to enumerate the languages so every language over 0, 1 was the ith language for some I. We already know how to enumerate binary strings, so we can talk about the ith binary string. Now, I'm going to define a language L. L is the language containing those binary strings W, such that W is the ith binary string. That must be true for some I, and W is not in the ith language. L is surely a language over alphabet 0, 1. Since we are assuming that the languages over 0, 1 are enumerable, that means that for some j, L is the jth language. So let x be the jth string. Surely some string is the jth in the enumeration of binary strings. Now we can ask, is x in L? It turns out that if it is, then it isn't, and vice versa. To see why, remember the definition of L. L contains W if and only if W is not in the language that corresponds to the same integer I that W corresponds to as a string. So let's focus on the case where W is x, the jth string. In that case, the value of I is j because we know x is the jth string. Further, we know that L is the jth language, so both
L, the language being defined, and the, quote, ith language mentioned in the definition of L are all the same, and they are LJ. Thus, when we read the definition of L as it applies to X, it says that X is in L, which is L sub J, if and only if X is not in L, again, which is L sub J. We have a contradiction. X is neither in L nor not in L. That's an impossible situation, and we conclude that our assumptions are wrong. The only unproved assumption we made was that we could enumerate the languages over 0, 1, so that is false. We can't enumerate such languages. As a result, we see that there are more languages than programs, since the programs can be enumerated. A particularly bad consequence of this fact is that there are languages for which no program can tell whether or not a given string is in the language. On the bright side, none of these strange languages are context-free, or therefore not regular, since the CYK algorithm gives us a membership testing program for any context-free language. The process of coming up with the language L that can't be in any enumeration is called diagonalization. The reason should be apparent from this picture. Imagine an infinite matrix in which the rows correspond to languages and the columns to binary strings. A 1 in the entry for row I and column J means that the jth string is in the ith language. 0 means it is not. If we could enumerate languages, then we could create such a table. Look at the entries along the diagonal and complement each one. That is, replace 0 by 1 and vice versa. Here's what it looks like. The complemented diagonal, rotated 45 degrees, looks like a language. It tells which strings are its members. Here, strings 1 and 2 are not in the language, the third and fourth are, and so on. But this language cannot be any row because it disagrees with each row in at least one position. In particular, it disagrees with the ith row in the ith position. We're now ready to look at the theory of Turing machines. One important purpose of this theory is to prove certain particular languages to have no membership algorithm. The first step is to prove certain languages about Turing machines themselves not to have membership algorithms. We're then going to introduce the important notion of a reduction from one problem to another. These are proofs of the form: if there is an algorithm for problem P, then there is an algorithm for problem Q. We'll draw this as Q is reduced to P. If we already know that there's no algorithm for Q, then how could there be an algorithm for P? Because if there were an algorithm for P, then this reduction would give us an algorithm for Q. Okay. By use of reductions, we don't have to resort to diagonalization or another trick to prove that P has no algorithm. Here is the picture of a Turing machine we should keep in mind. There is a state which, like all other automata, can only be in one of a finite number of states. There is a tape, this, infinite in both directions and partitioned into squares, each of which can hold a symbol of a finite tape alphabet. There is a tape head that always points to one of the tape squares. The Turing machine makes moves just like the finite automaton or pushdown automaton. For the Turing machine, the move is determined by the state and by the tape symbol under the tape head. In one move, the Turing machine can change its state, write a new tape symbol over the old one in the square its head is scanning, and move the head one square left or right. We might ask why we introduced the Turing machine rather than representing computation by C programs. While you could develop a theory around programs without using Turing machines, it would be much harder. The thing that we'll come to appreciate about Turing machines is that they are so simple in their operation compared to programs in a programming language or even real computers. That wouldn't matter if Turing machines could not mimic real computers, but they can, as we shall argue. And in fact, one could argue that because Turing machines have infinite storage capacity on their tape, they are even more powerful than computers, since computers always have a finite amount of storage, however large that may be. But the difference is not essential, since in principle, We could always buy more storage for a computer. One could counter-argue that the universe is finite, so where are you going to get the atoms from which to build all those disks? But even if you accept that the universe is finite, the limitation doesn't seem to be affecting what we can compute in practice, so we're never going to argue that a computer is weaker than a Turing machine in a meaningful way. So here's the formalism we'll use for Turing machines. There's a finite set of states, and we'll follow our tradition of using Q for this set. There's a finite input alphabet for which we use the traditional sigma. There's a finite tape alphabet, gamma, which always includes the input alphabet. The transition function is, as always, delta, and we'll talk about how that works next. There's a start state Q0, a member of the set of states Q. Again, this is as before. There's a blank symbol, which we usually represent by capital B. This symbol is in the tape alphabet, but is never an input symbol. And there's a set of final states, F as usual. And there are several conventions about letters we shall use. They are consistent with our earlier conventions for finite and pushdown automata. Lowercase letters at the beginning of the alphabet are still symbols of the input alphabet. Now, capital letters at the end of the alphabet are tape symbols, which might or might not be input symbols. Lowercase letters at the end of the alphabet are strings of input symbols. Again, that's as usual. And Greek letters at the beginning of the alphabet are strings of tape symbols, which again may include some input symbols. Now let's see the transition function delta for a Turing machine. The Turing machine is deterministic, and moreover, it does not have to have a move in any situation. Delta takes two arguments, the state and the symbol scanned by the tape head. Delta of QZ, for state Q and tape symbol Z, can be undefined, in which case the Turing machine can make no more moves scanning a Z in state Q, and the Turing machine is said to halt. But if delta of Q and Z is defined, then it is a triple PYD, where P is the new state, Y is the symbol that replaces Z in the square being scanned on the tape head, and D is the direction for the tape head to move. This direction is either L for left or R for right, and the move is by one square. Here's an example of a Turing machine. Its input symbols are 0 and 1. The Turing machine scans right on its input looking for a 1. If it finds a 1, it changes it to 0 and goes to a final state F and halts. However, if it sees the blank symbol before seeing a 1, it changes the blank to 1 and moves one square left, repeating the process just described. There are two states for our Turing machine, Q and F. Q is the start state and F is the final state. As we mentioned, the input alphabet is 0, 1. The tape symbols are only 0, 1 and the blank B. One move of the Turing machine is given here. It says that in state Q, scanning a 0, in state Q scanning 0, it stays in state Q, leaves the 0 on the square it was scanning, and it moves right. Another rule says that if it is in state Q and sees a 1, it goes to final state F, replaces the 1 by a 0, and moves right. It doesn't matter which way the head moves in this situation since it has accepted its input, but it always has to move left or right, so we'll say right. The last move of the Turing machine is this. It says that in state Q, while scanning a blank, it replaces the blank by 1 and moves left, staying in state Q. Here's the beginning of a moving picture of this Turing machine. The three moves are shown in the upper right, with the move that is applicable in a given situation shown in red. Here, the Turing machine has just started. It is in its start state, and the tape head is at the left end of the input, which is 0, 0 in this case. That is, here's the input. The rule in red says that in state Q, scanning 0, it moves right and leaves the state and symbol unchanged. So we'll see that on the next slide. Here it's done that, and it is in the same situation, again scanning a 0, so it again moves right. Now it sees a blank on its tape, so another rule is applicable. This rule says that stay in state Q and replace the blank by 1 and move left. So it's made those changes, and the first rule is applicable again. The Turing machine is going to move right while leaving the state and symbol unchanged. Here the second rule applies. In state Q it is scanning a 1, so it goes to the final state F, replaces the 1 by 0, and moves right. Here we see the effect of the last move. The Turing machine has no move for when it is in state F scanning a blank, so it halts. It has also accepted since F is a final state. Moving pictures of a Turing machine can get a bit cumbersome, so we're going to develop an instantaneous description, or ID notation, for Turing machines similar to what we use for pushdown automata. But in a sense, the Turing machine IDs are even simpler because the input and tape contents are combined into one string. Moreover, we represent the state and the head position by embedding the state to the left of the symbol being scanned. We'll always assume that state symbols are chosen so they do not conflict with tape symbols, and thus we can always tell which symbol is the state. As we suggested in our little example, the Turing machine gets its input on the tape. The input, which is always a string of input symbols, is placed on the tape surrounded by an infinity of blanks to the left and to the right. The Turing machine begins at its start state with the head at the leftmost input symbol. If the input string happens to be epsilon, then the Turing machine's tape is entirely blanks and the head is scanning one of them. An ID is a string of the form alpha, q, beta. Here, alpha beta is the contents of the tape between the leftmost and rightmost non-blank symbols. That is, the tape consists of an infinity of blanks, alpha, beta, and then another infinity of blanks. We should observe that after any finite number of moves, the Turing machine has only visited a finite number of tape squares, so there can only be a finite number of non-blanks. Thus, we always have a finite representation for the tape, even though it is infinite in extent. The state is Q, and it is placed immediately to the left of the symbol the head is now scanning. Remember, we assumed state symbols are chosen, so none of them are tape symbols. Therefore, we can always identify Q. As a special case, Q can be at the right end of beta. If so, it means that the symbol being scanned is a blank. This can only occur if the Turing machine has just moved to the right and there are only blanks to the right. We use the turnstile notation, that is this, to represent one move, and we use the turnstile star, this, to represent any number of moves, including 0 moves. These are exactly as for PDAs. Here's an example which corresponds to the earlier Turing machine example, but now using the ID notation. We start off in the start state with the state to the left of the input. At the first move, the Turing machine moves right, here, and then right again. Now it is scanning a blank, and its action was to replace the blank by a 1 and move left. Notice that the state is now 2 symbols to the left of the end, and it's scanning what used to be the rightmost 0, that is this guy. It again moves right, and when it sees the 1, it enters state F and again moves right, changing that 1 to a 0. Now we'll discuss the turnstile relation formally. We have to discuss what happens on rightward moves separately from what happens on leftward moves. So suppose there is a right move where in state Q, scanning a Z, the Turing machine goes to state P, writes Y, and moves right. Then in any ID with QZ as a substring, which means that the Turing machine is in state Q and the Z is being scanned, we can replace QZ by YP. That has the effect of moving the head right, as well as making the state and symbol changes called for. There's a special case when Z is blank. Then it is additionally possible that from an ID with Q at the right end, that is this, which means that a blank is being scanned, for the next ID to replace the Q by YP. That is, the blank which we didn't see in alpha Q has been replaced by Y, that's here, and the state Q became P, P of course moving to the right of the Y that it just wrote. Now consider a left move, where again we are in state Q scanning Z. The new state will be P, and the symbol Y will be written over the Z. If there's any symbol X to the left of the state in the current ID, such as this, then in the next ID, the Z is replaced by Y, and the XQ is replaced by PX. That means that X is being scanned in the next ID, and of course we have gone to state P from state Q. But we also have to take care of the case where the ID has nothing to the left of the state, which means that there is an infinity of blanks to the left of the present head position. Then we reflect the move by replacing the Z by Y, that's that, and introducing a blank to be the symbol immediately to the right of the state. It's okay if the ID represents a blank explicitly, and this is one of several situations where we have to do so. However, it is important to note that the length of the ID can only grow by 1 at each move, so it remains finite after any finite number of moves. There are actually two ways to define the language of a Turing machine. Final state is one of these ways, of course. Formally, L of M for Turing machine M is the set of strings of input symbols W, such that started in the initial ID, that's Q0 W, with W on the tape, M gets to some ID with a final state. The other way to define a language is by halting. We define H of M to be the set of input strings W such that started in the initial ID again. M gets to some I for which no move is possible. The two methods of defining languages define the same class of languages, as we can show by simple Turing machine constructions that are not too different from how we show that PDAs accepting by final state and by empty stack have the same language defining power. Given a Turing machine M, we're going to modify M into a new Turing machine M prime. The language M prime accepts by final state, M prime will accept by halting. We can easily make the final states of M be halting states by removing the rule for delta of Q and X whenever Q is a final state. But we have to protect against the possibility that M halts without accepting, because the M prime would then accidentally accept. So for M prime, we introduce a new state S, whose job is to make sure M prime never halts. Once M prime is in state S, on any tape symbol X, M prime stays in state S, leaves the X as it is, and moves right. Thus, M prime will always have a next move in state S. Eventually, it will get to the infinity of blanks to the right on the tape and look at them one at a time. And to make sure M prime doesn't halt accidentally, whenever delta of Q and X is undefined for M, and Q is not a final state, we'll have M prime enter the state S. The construction in the other direction is also pretty easy. Now we assume M accepts some language L by halting, and we want to modify it to become M double prime, which accepts L by final state. We introduce a new state F, which is the final state of M double prime. F has no move, so in fact M double prime will also halt when it accepts, but it doesn't matter. Once a Turing machine enters a final state, if acceptance is by final state, then nothing it does in the future will negate the fact that the input was accepted. If M halts in any situation, that is, delta of Q and X is undefined, then define it and make the next state be F. We now have a proof that the class of languages accepted by Turing machines using final state is the same as the class of languages accepted by Turing machines using halting. The name for this class of languages is the recursively enumerable languages. You might rightly wonder where this name came from. It actually predates Alan Turing's paper describing Turing machines, and it refers to an earlier notion of anything we can compute. I'm not going to say more about that. But there's another important class of languages related to Turing machines. These are called the recursive languages. These, we shall see, are a proper subset of the recursively enumerable languages. An algorithm, formally, is a Turing machine accepting by final state that halts on any input regardless of whether that input is accepted. This notion of an algorithm is consistent with the informal notions you may have learned. However, it is limited to acceptance or rejection of input. That is, all algorithms in this sense render a yes-no decision but do not compute an output. We can extend the notion of what a Turing machine does to allow it to produce output and then halt, in which case we have exactly the same notion of algorithm that is taught in freshman computing. A language that is accepted by final state by some algorithm is called a recursive language. This term too comes from the history of attempts to answer the question, what can we compute, prior to Turing's insights. For example, every context-free language is a recursive language. You can implement the CYK algorithm for any context-free language on a Turing machine. That Turing machine will halt once it has computed the triangle of sets of variables and checked whether the start symbol of the grammar is in the final set. But the recursive languages go way beyond the context-free. In fact, it is very hard to come up with a language that is not recursive, except by using tricks like the diagonalization we discussed earlier.